of my team. So very good morning to one and all. Coming to chemistry in space technology, let me thank the organizers on the start at the outset, and let me get into the title. Title is today is chemistry of space technology. In this, I am planning to cover the propellants, because chemistry is there means wherever chemistry is there, propellants, chemical materials based on polymers and ceramics, and energy systems, which are chemical systems which are delivering electricity to the any power supply is there, means automatically this is the one which powers. That is also based on chemistry, and it goes without saying that without analytical methods like diagnostic methods for chemicals, this is the like our diagnostic laboratories for human being, analytical laboratory is the laboratory for the materials. So then over to life support systems, that is the futuristic missions for India, but already the human space missions, whatever we are doing there also, what all supports that we will be able to give where chemistry is important, and planetary missions also will be covering. So the left side, if you look at it, it is the typical launch vehicle, because the letters you will not be able to see because it is so small. I only wanted to make that this so critical and complex systems will be there. On the right side, it is satellite, where the systems are all portrayed. So I'll come to the explanation. That time you will understand. And whatever above is seen is the reusable launch vehicle of our Indian pride is this one, and we are coming up step by step. So where chemistry is also playing a role in that direction. So coming to the space technology, what all space technology involves means you all know that there should be a vehicle which will be reaching the space through accessing the space. So we need a vehicle which normally carries satellites, spacecraft, astronauts, and any payloads. So whatever interest experiments what we are doing on Earth's atmosphere we have to study means we need a vehicle, and that vehicle will be carrying the instruments or the satellites which will be staying in orbit. While moving, it will be having a synchronously positioned in orbit. So the satellites and spacecrafts are essential. These are the two items which are carried by launch vehicle. So what is the purpose of these satellites means it is to observe the Earth, general positioning system, scientific research, then planetary exploration, and beyond Earth, right, we have to go means Mars, Jupiter, and the Venus, including Aditya mission we have slated. And if that is, these are all the deep space observations we have to go means these missions are essential, for which all these things invariably will have propulsion system. Basically for the launch vehicle, the thrust, Newton's third law is completely in work. The chemical energy will be converted into heat energy that will create a pressure. That pressure will be controlled by directed so that we get the thrust for a forward movement. Then definitely spacecraft also in a smaller order we will be doing it, but over a long period for maneuvering, orbital maintenance, such requirements also propulsion will be required. Then, so to say, without electricity, nothing moves in the world. So we have to have in the space, and wherever the power transmission is not possible, we will have to carry the battery and solar cells. Sun God will be providing the solar energy. So that light we will have to convert into electricity, and that electricity will be stored in battery. And then automatically, now that man is not completely satisfied being within the Earth, so we'll have to have human in space. So if that is the case, we'll have to meet all the requirements of the daily requirements of a human. Then for that, including starting from the prana, that is oxygen, to taking care of the carbon dioxide and its own daily requirements means automatic life support systems comes. So everywhere we'll have to have the chemistry means automatically the components which form space technology like communication systems are there, navigation and control, and harsh environment. All these things have to withstand like a hot vacuum and very high temperature. The radiations, electromagnetic radiations will be there. And so to say, now the debris are much more than the items which are rotating, that is spacecrafts. So meteorites hit, all those things will be there. So it is much more a traffic jam that is likely to come in future. So how we will be able to face the harsh environment during launch, being there in the orbit, and while being there in the orbit, we will have to also escape ourselves from meteorites. So for all these things, how the chemistry is going to be useful, and the instruments, scientific instruments we will be carrying, those are also for chemical aspects we will be carrying. So I'll briefly go ahead. So automatically, all of you know that especially the youngsters who have joined here in the program will be understanding that this is a periodic table. You can see different colors. The colors means the vertical one color is there, then horizontally colors are there. So these are all meaning starting from hydrogen to now that we have about elements named already up to 118 are named. Okay, so these are all the rows and columns. So this is representing the number of electrons based on the electrons like s orbital, p orbital, and d orbital. And d orbital starts from 3 onwards, and the 4 onwards f orbitals will be coming. So that is the case, means automatically it will be 5, 6 up to that level we will be going. So we have actinides and the lanthanides also being there. So all these colors represent, one is the like group is there, first group, then colors, all these things, you know how the categorization is done. So these are all the transition metals where you will have more d orbitals. Then once you come here, this onwards it will be lanthanide. Then these are all post lanthanides, these are all actinides. So you will have f orbitals being there. So we have enough electrons, each electron plays a role, all of you understand. So if that is the case, so what is that we are going to do with the chemistry? The chemistry means definitely all of you will remember there is a bond. Bond means bonding. Bonding means two people should come together, means it is a bonding. That's what it's called. So here, two people, you can see the hydrogen and oxygen being portrayed here. So H and H, it's a bond between two similar atoms. O and O, this is a bond between the similar atoms. If you see the H2O reactant, if I am saying, there is a bond between H and O. So what is the use of this bond? Bond is nothing but kind of without breaking or forming, we cannot have the chemistry being run. And in that process, why we have to have an indus means automatically the bond is associated with an energy. And if what is the energy required to break a bond depends on the atoms. That I will come to that. So that is what is the energy required to break the bond or to form the bond. There also the energy is associated. So the individual atoms and the atoms to which this is getting bonded, all of them are important. This is what is forming the fundamental basis for our chemical reactions, chemicals and composites, energy systems, propellants, polymers, all non-metallic materials which are very, very essential, including oxygen, what we are inhaling, it's coming out as carbon dioxide. So the biological reactions are taking place, but definitely it is these are the two simple chemicals without which not even for a minute we will not be able to survive. So now the bond is the one which we'll have to start with. So the bond means automatically, what was the use before going into the actual bond characteristics? I'll display some of the events which were where chemistry was playing a greatest role in understanding the space technology. So as I was telling, launch vehicle is required, then spacecraft is required so that we can go to moon or we can go to Mars. As you all know, remember, recall yourself, Chandrayaan 3 on course to moon. So in the days to come, it will be landing. So India will be making a step through our lander in the days to come, especially in the month of August, we will be doing it. If that is the case, we have also done it. So in order to simply understand the role of chemistry for space technology, you may all remember that there was maybe history. If all of you, if you are younger, means then you will not be knowing, you will not understand the thing. But if you read books, automatically you will get in 1986 the famous space shuttle on takeoff got exploded, and unfortunately the 7 crew also died. So then people were not knowing what happened. Everything was tested here. What was the problem they were hampering, and it was how the total vehicle got ripped off. They were thinking at that time only the famous Professor Richard Feynman came out that everything, all assembly, everything was taking place in room temperature of the order of about 25 degree to the 30 degree. But the O-ring which was used to seal the connection where we were, the pressurized chambers will be there. Once it was exposed to 0 degree, it got contracted. So once it contracts, the sealing was lost. The sealing is like all of you also would have come up in the scene in the house, there will be a seal in the tap. If the tightening is not done, there will be leakage. And over the time, if the compression is getting locked, it will not be compressive enough, then leak will come. So here what happened, the O-ring got subjected into the contraction because of the 0 degree, then it gave way to leak. The hot gas was coming out, the hot gas got into the hydrogen tank, then hydrogen tank blasted, so nothing can be saved from that. So this was the first incident where the people got to know simple chemistry and with respect to the material which is having the characteristics of nature, then they changed over to a different material wherein the bonding was not getting contracted, such a material was selected. So basic understanding of the chemistry was only helping to overcome the problems faced in the Challenger. There was a great lesson learned. Before that also lessons were there, but this was the greatest lesson, the simple chemistry, how it was giving solution for the further things. So then yet another thing was that when the Apollo people got into the moon, once they were having a round, then they had to come back. Before landing, the several experiments were taking place. The Apollo 11, the oxygen tank got exploded. So now they have to survive without the oxygen tank. So now the carbon dioxide also will not be, once it got exploded now, this is the total system had to be restarted. So they were not knowing what to do, because the carbon dioxide, if it is filling the cabin, so they were having lithium hydroxide canisters. Then some chemists were there, or chemistry was there in their mind. So that was helping them how to remove the carbon dioxide. They exposed the room to lithium hydroxide canisters. Automatically carbon dioxide got reacted and lithium carbonate was getting precipitated. That is one. So there was a residual charge, again the chemical material which was generating the electricity and providing to helping them to restart the crew module. So with electricity and carbon dioxide being removed, they were able to manage and they could reach back in the earth. So this is yet another chemistry role. The major roles only I am giving. There are several and innumerable roles are there. So, but I am not getting to all of them. So coming to innovations. So whatever we are developing for the space, several things there we had a spin-off. That is the costly items what we are developing can also be going to societal use. So that way chemistry has got a kind of wide and very strong applications. And these are all the areas where the innovations have come out through chemistry, adhesives, polymer plastics, propellants, and chemical. So not only that, the origin of universe through chemical way only we can understand based on the molecules that are present in the environment or atmosphere of that particular planet and how the climatic conditions are getting affected. So only carbon dioxide what we are facing now because of the carbon emission, we are all getting into problems. So like that, the issues are coming up. So a little more onto the chemistry background. So I am mixing the events in chemistry so that it doesn't become a class of chemistry. It is chemistry in space technology. I love to communicate to you means automatically these are all things. So just to recall, so these are all the red color, all hydrogen-based compounds. So you can see the right side, whatever I have given is the bond energy in kilojoule per mole. If HH is there, it is about 432. Same thing if it is carbon-carbon, it is 347. Go to NN, it is still simply 160 only, right? So depending upon the elements, the bond energy varies. That is number one. And the same hydrogen, if it is fluorine, the most electronegative element, the value goes up. That means the bond energy is increased because there is a sharing of electron. The electron is pulled by the fluorine, then it becomes higher. And then you go down the group. If it is fluorine, same halogen, it is going down. So that means the same atoms will have a different energy and different heteroatom when it comes also depending upon the atoms, the energy will keep coming down. One aspect is there because in the group, the atoms are coming down. And depending on you come to carbon, the trend will not be like that. The CH 413, then CC it will be like that. Say carbon fluorine, if you see it, it is still more. Similarly, the values. So that means different type of bonds, different type of atoms will give different bond energy. That is one point. Then come to oxygen, the similar trend will be there. So we can see the variations. Then there are some things like multiple bonds. So different atoms will give different kind of, for the same cations, you will have different anions if you are having, automatically you have bond energy variation. And between the same, we can have multiple bonds also, not only single bond, double bond, triple bond. You see here, carbon-carbon 347, double bond it is 614, triple bond 839. Same oxygen if you see here, it is 614, it is 495. So it is nothing but sharing of electrons, number of electrons involved, and number of electrons associated in the particular atom. See, it is carbon, next it becomes nitrogen and oxygen. Within that itself, now you can see how much variations are there. 839, 418. If we compare the double bond 614, here the double bond 495 only. So depending upon the pattern of arrangement of electrons in that particular fashion and the materials involved, the bond energy varies. So this is what is the first thing. So automatically, without breaking the bond or without bonding, breaking and making gives the energy storage as well as the energy absorption. See, if reactants, if I am giving energy, I'll get products with more active energy. So that's what is the point. So for space applications, no, like we have seen this kind of variations. Variations means one is propellant. I'll straight away go to propellants with this chemistry background. The different atoms with the same kind of atoms also the bond energy will be different. If I have to get energy or store energy into a system, I will have to choose particular materials so that when I am breaking, the energy is released, and we'll have to specifically make the materials. And these materials, no, these kind of the propellant materials, if I am able to control and on a violent burning, if I am able to give it out through this kind of a Newton's third law comes into picture, I will get the thrust. So the launch vehicle or the rocket will go up. Then if you see some of the other things, there will be some sudden release of huge energy. A huge energy means the rocket will burst. So, but where this I think used, like all of you will remember the matchstick. Once you do the mechanical operation, automatically it will give rise for instantaneous flow of energy will come out. There we cannot control, but we can use these things for our pyro activities, wherein the simultaneous actions have to take place. I will have to remove this kind of expanded stages, means we use this kind of explosives where uncontrolled sudden release will be there, but in a small quantity. So it will be a local explosion will be taking place. So you come to pyrotechnics is yet another thing. In order to ignite these pyrotechnics, we use the explosives, and the pyrotechnics will be giving the energy out to remove the stage. So this is something like our crackers. So in the chemistry, we can have the bond, depending upon the material that we bring in, we can make use of the applications for space applications, the space technology. So we have been developing solid propellants, liquid propellants also. That means solid means materials, both the oxidizer and the fuel. So one is the material, because the energy can come out only when there is an electron transfer takes place. So electron transfer means, as I was telling, the particular bond is to be broken, and some other bond with lowering energy should be formed, so that we get heat energy in the form of heat energy, which will be propelling the rocket. So here oxidizer is the one which will undergo reduction. Fuel is the one which will donate electrons, which will undergo oxidation. So when these two are the particular specific materials are mixed, means automatically the spontaneous reactions on ignition, it will be delivering a lot of heat and low molecular weight gaseous molecules, hot gaseous molecules, nothing but pressure. If that pressure can be oriented towards, as I was showing in the previous slide, we will be getting the thrust to reach or access the space wherein we can deliver the payloads. So you understand? So I'll come to an example wherein the solid materials can be used as well as liquid materials also can be used, because the energy content. Some of the liquid items where we can use it as a monopropellant, some of the items we can have bipropellant and cryogenic propellant also. So I'll just explain what are these things. I'll just draw draw the attention to, if you take a car now, 1 horsepower, about 745 watts, and any typical car is of the order of about 90 to 100 horsepower we are putting in. It is just using a petrol or diesel. In these two are the fuel materials, and oxygen is nothing but our normal oxygen from air, 20% of air that is coming from. At the same time, if I have to have a train automatically I don't need to say, because nearly about 700 to 800 people, several tons have to be pulled. So the order goes up nearly about 90, becomes another 40 times. And if an aeroplane, it is in the 5th order, and if it goes to rocket, so this is the speed with which we will be able to get it. So it goes to 37 million. And the flow rate of the fuel and the velocity with which it can go is narrated here. Nearly 36,000 kilometers per hour we will have to go, means this is the kind of energy that we will have to get. Accordingly, we will have to design the material. Accordingly, we will have to also make the design of the solid propellants embedded inside a stage. So now I'll give a little more details with respect to solid propellants, wherein the oxidizer and fuel, what I was telling now. Here, typical oxidizer is ammonium perchlorate. So ammonium perchlorate means automatically the perchlorate ClO is in the 7+ oxidation state, and that is ClO4 will be having NH4 plus, ClO4 minus and NH4 plus, and that will be the oxidizer and metallic aluminum powder with the polymer binder. See, without that, see, this is what a typical microstructure in the blue color. The yellow one shows bigger particles of oxide, the oxidizer, that is ammonium perchlorate. Whatever is in the violet color is the aluminum fuel particles, which are smaller in nature, and these two are held together by a binder, which is nothing but that is a polymer material, wherein it's a long chain molecules are there. That is also another chemical bonds that are coming in. All of them together. This is unit area. This may be about micron size, which I have bloated now. So they are all bound by a binder. So now, example wise, if you take oxidizer, about the major portion will be there. Metallic oxides will be there as catalyst. This will be the binder, and this will be the fuel like aluminum. So these things are together. Once you ignite, there will be a kind of a heat generated. That heat will further melt this HTBB, which is in the form of polyurethane, and then keep on exposing the fuel and oxidizer that we are continuously getting. So this is the stage where it is filled with the propellant in the form of a solid, which HTBB as the binder, aluminum and ammonium perchlorate will be there. So here is the nozzle, which will be red hot when it is the propellant is burning, and automatically this will have a forward motion. So with that, let me go to the status of our level. Ours is the left top S200. We generate about 600 ton thrust using a 200 ton loading of propellant. You can see all others also. This is with respect to Ariane. This is with respect to space shuttle, where 500 ton is required, where 1500 ton thrust they will be able to get, and space launch system also of the order of 630 you will be getting, and these are all the different status. So we have come up to 200. We can also go beyond that one also. So come to liquid propellant, where both the oxidizer and fuel will be liquid in nature. So oxidizer is of the is what we call it as this is hydrogen. Oxidizer is N2O4. Hydrogen is in the UDMH, that is unsymmetrical dimethyl hydrogen will be there to add the energy. So both of them, one will be fuel, another will be oxidizer. Once the liquid is there, we will have to pressurize it for the required mass flow. Then we need pressurization system through the turbo pump, as well as gaseous pressure also will be there. So by these things of solid, liquid, all those things we need is solid with the exhaust velocity of, because the chemistry and the kinetics is in a position to give about 2.5 km/s level, and the propellant mass will be of this one. The specific impulse is that the energy produced per kg and the speed with which it will be able to produce the energy will be of the order of about 270, 280 level. So you come to bipropellant, liquid will be able to give a higher value of about 300 and 310. And cryogenic, that is cryogenic means we'll have to go to a very low temperature, where hydrogen oxygen, when we are using it, to be offering us a very high temperature. It's only simple hydrogen and oxygen, but in liquid form, we will get a level of about 450 ISP per second we will get. So these are all the different type of liquid propellants to get higher and higher energy. And once liquid is there now, automatically we will have a better way of handling. So simultaneous oxidation reduction is combustion, and high energy delivery is the order of the requirement, and high rate is required. So this is the kind of small mechanism. High oxidation reduction should come. The products will be getting formed, and it is the electron and proton transfer which gives rise for these are all the products that are getting formed in the system. You can see we started with only chemicals, few chemicals, but so many of gaseous molecules are formed in the hot condition. So the energy comes from the fuel and oxidizer, where the bond is broken. New bonds are formed with lower energy. The heat energy is coming out from the bond breaking. So that's what is giving you the energy. So these are all just example when we are at the kitchen now. Biomass, this much only it will give. Flame tube is very high temperature. Solid propellants will be much higher order it will give, as well as with the smaller quantity of material. Okay, so let me go over to give you a little more complexity. So not only this one, automatically we have a catalyst material, we have melting and vaporization as mechanisms on the way, and vapor phase mixing will have to take place. So these are all the intricacies which are to take place for us to sustain a uniform burn rate and uniform thrust, so that we are in a position to reach the required orbit level. That means we will have to go against the gravity and attain certain velocity, so that when we are reaching 300 km or 400 km, or with a higher velocity at 200 km itself, if we are doing, we will go to eclipse, we will have an perigee and apogee. At that time, we will be able to reach the desired orbit. So here, the catalyst also plays a role. Suppose if I take iron oxide, just to give a feeling, if the particle size or material is, if it is gamma, this is what is the burn rate that we will be getting, we will be reaching the altitude. But when it becomes nanoparticles, high surface area, we will get still higher. So morphology itself is giving you better and better efficiency, just to give a bit of an understanding about not only the chemicals, and its morphology also will come into picture. And we can also have some kind of additives to enhance the catalytic role. Even if the coconut oil with the nanoparticles are there, still higher aspect will be. So that means facilitating the bond to work well to our advantage, to get some of the capabilities out. So this is what, then with having said all these things, I'll have to come to little physics for you. Without that one also, the chemistry alone cannot go. With the physics and chemistry should go hand in gloves, so that the physics people are able to use the chemical aspects, chemistry people are able to use the physical aspects. So ISP is the one, it is the force per time and what is the amount of energy that is released. So then it is, in other words, it is the TC, that is the flame temperature, and the number of molecules that are getting. So now Ft by W, that is the vector, the power vector or energy vector, is directly or equivalent to the Tc by m, the temperature that is generated by the chemical, and the more low molecular weight are getting formed means automatically we will get a higher ISP here. So that is what is the idea. So this table is comparison. Again, I am repeating for your understanding purpose. Then just to know that future formulations of propellant, how we are going to do, as I was mentioning, the fuel are normally starting with more hydrogens. Oxidizer will be using the oxygen-based materials like hydrocarbons here, like even kerosene, or kind of our liquid methane kind of materials will have hydrogen-rich molecules will provide. So with water or kind of things are to be formed means automatically we'll have to have oxygen derived. This is what is the perchlorate, dinitramide. So here, as I was telling, the particle size and higher loading also will decide with respect to the ISP level. And we can have both the fuel and oxidizer in the same material also. So this kind of organic molecules can be. So now the design of material is depending upon the way in which it will be able to deliver. That means there is a term called heat of formation or heat of the reaction. The reaction means automatically the H, delta H should always be negative. All of you know that if delta G is to be negative, we should have delta H, that is the bond energy associated with the products and reactants. Automatically the reactant should always be higher, so that the products are having a lower heat of formation. So then the delta H becomes negative, and once the negative, if it is there, automatically we will be delivering more energy. So once the reactants are having higher level only, we will be able to get the products at a lower level. So the delta becomes the energy, quantity of energy released. All of you may be knowing, or please get to know, this is the reaction progress rate which will be delivering the energy. That is nothing but breaking the bond and making the bond in smaller molecules. So both will get the association with energy. So with that, these are all operational things. When I have to make the propellant working, so we need a motor case, we need insulation and inhibition, because whatever propellant is burning, it should not affect the motor case performance. So that is also important. When you have to think about a system, safety is very, very topmost interest. The quality, safety, and the system, all three are like forming the three points of a triangle, wherein each one is important for us to make space systems. So with that, now with the propellants, let me move over to what are the other materials which are essential for the space requirement, because all of you know space is no compromising situation where the ultra high vacuum will be there. If this kind of low molecular weight materials are there, a lot of outgassing will come out. The outgassing means loss of material. The system itself will lose the material, and not only that, the material which is coming out as a result of outgassing should not get deposited like our payloads. Like we will have a camera, we will have mirrors, and these materials, if they are getting deposited on to the payloads, means automatically it will be getting masked. So having gone to space and this kind of performance inferiority, if we are getting into, we are subjected to means and we lose the total objective. And we need to have these materials to somewhere from 20 Kelvin, what I was telling now, minus 200 to at least plus 100 degree, it should meet the requirements of space, demanding space requirements. And as I was telling, radiation also will be there. And atomic oxygens, because it is vacuum and the high vacuum is there and no energy will be there. So atomic oxygens can freely move around. Even 10 power 19 atoms, because 10 power 23 atoms only will form your 1 mole. But here it is even suborder level atoms in a square centimeter itself will affect the space systems. So our systems should be resistant to attack by the atomic oxygen. It is only the chemicals and the chemistry which is the imagine, and we are able to inculcate or incorporate into the system will withstand the atomic oxygen attack. Solar radiation will be there, micrometeoroids which I was telling, then so many debris are flying. So all these conditions, if it has to meet in the launch vehicle, we need to have chemical materials which are of different nature. So as we all know, it is mainly it is polymeric materials, carbon-based materials which we have exhibited here. That is polybutadienes, polyurethanes, polyimides, polysiloxanes, nothing but silicones. Then epoxy, it is kind of araldite family of materials, and phenolic resin, like this is like our bakelite materials are there, no? Iron sheets, no? There you will have a very strong material, stiff, it will not be bending or will have no flexibility. So all type of materials are there. Then why this many materials and how we are getting it is the intriguing question that must be there in your mind. If that is the case, automatically I will go that these non-metallic materials play a crucial role in space arena. So these are the materials which we will have to deal, starting from propellants and polymers and ceramics and composites, energy storage systems, life support systems. And to analyze, understand the composition, the composition of the raw materials, and once the product is formed, the right product is formed or not, we will have to come to 150% confirmation. We will have to verify. Then only we will have margin. So no failure condition means zero defect is really zero effect. It is not 0.001. It is completely at least 10 power minus 5, 10 power minus 6 level reliability is required. If that is the case, we need to understand. And a lot of tests will be carried out. So for which the failure analysis, but also the chemical methods are to be there so that we can understand the course of failure or mode of failure. So everywhere the chemistry aspect is there. So this is what I would like to give you, why this different set of chemicals are required. This is like, all of you know that normally we see HCl or kind of sodium chloride, only one bond will be there. But here the polymer, as you know, the repeated units of the same the single unit is only polymer. So unless we undertake the polymer, all of you know carbon. It is like our carbon dioxide also is there. It is a gaseous material. And all of you understand the polyethylene, our carry back what we are doing, polyethylene. So that contains chain of carbon and just hydrogen atoms will be there. But that will not be sufficient for us. We will have to make use of so different material means we need 2 ends polyol so that it will react with some other chemicals to form rigidity. There can be parallel cross-linking. So now why these heteroatoms oxygen is brought in is that this is what is end OH is called polyol, and this is ether ring. ROR is the ether. If I am having ether alone, I am having certain properties inherited. So now I am simply introducing a keto group here, in addition to oxygen. So that means this area, as we were understanding the bond, carbon-carbon bond is there, carbon-oxygen bond is there, but here the carbon is having one oxygen with single bond, another rigidity for the system. That's how we modify the materials and the functional groups to get the desired properties of meeting the harsh conditions. Then you go for a polycarbonate. Together, the unit is completely engulfed. Not only here, 2 alternate things. You have a long chain as well as a carbonate also into it. Then it becomes a polycarbonate polyol. Then you introduce another heteroatom that is called N with a group of carbon atoms variation. Like this is also a group. Another thing. This is called diamide. So it is a urethane, polyurethane things will be getting added to that. Then we will have isocyanate, means we will have another urethane also. So that's how the making and of different bonds of different nature gives us different bond energy to the molecule that is able to withstand the structural load, thermal protection, then this sealing requirements like flexibility, like that. So here is the one where I am like I was telling you, how this energy. I can also have variations here. You can see the numbers 62. Sorry, back no. Yes. Yeah. 62, 63, 64. Depending upon the bonds that are added or branched, I'll be able to vary the number here. You can see the bond strength, how it is varying. So it can be tuned. So chemists can also do the tailoring job of individual atoms and molecules so that we are able to tune, correct? So here the same logic we can also bring in for layers, graphene layers, then the graphene, and we can also add some of the solid materials into the matrix so that the rigidity as well as strength goes up. And also now we have been using so far, like people were only looking forward to high energy materials, but some of the high energy materials are also the emerging to be a toxic, even affecting the space kind of conditions. So now that we'll have to make a different type of bond, somewhere like H2O2, hydrogen peroxide, hydroxyl ammonium, and the ammonium dinitramate kind of materials, they do not they release like the toxic gases. So whether it is synthesis here or after usage, we are leaving it into the atmosphere, we will be able to overcome. So making the energy and also green way is the order of the day. Like all of us are getting over to, we are not going to use the petrol and diesel. We are all going to have the electric vehicle. So that is going to be a green way of making it. So there again, chemistry comes into picture to same making and breaking bond between different types of atoms. We'll have to tailor it. The way the nature has formed, the long way, the cellulose materials we are burning and the dumping the carbon dioxide, which causes climatic changes, deforestation kind of thing. Then another thing also what I am showing is this is a dynamic chemistry we can have. So wherever the systems, whatever we are having, this is the line is nothing but a crack that is getting formed. So we can incorporate some of these materials which is enclosed, like you can see here, the sulfide cross-linking is there. Disolved reaction you would have gone. So now nitrogen-rich materials with the complex is also there. So the ligands are engulfed into the coordination materials, coordinated complex. So once there is a crack, these materials are getting exposed, then it releases the reactant in situ. So that in situ is able to get healed up, right? So once there is a crack, the materials are exposed, then it is able to bring in the new bonds in situ. So that facilitates or brings out the self-healing aspects. So like that, we have variety of materials. This is like carbon chain with the double bond I am bringing in. This acts as the binder material for our solid propellants, S200. This is S200. This is another S200, nearly about 400 tons. We are having in that one 40 tons of binder will be HTBB. So this is what is the reaction. This HTBB on with isocyanate will give rise to a polyurethane. That gives the rigidity for giving the strength as well as acting as the fuel, part of fuel. So next I will move over to the benzene rings. There is a polyurethane I was telling. We can straight away take the polyurethane. Here benzene rings can be added in the chain so that rigidity will be more. So this emerges as kind of the very good thermal insulation materials. It is not permitting the heat to flow through and also maintain certain rigidity. So these are all the kind of rigid forms, flexible forms, low density flexible forms, and hard solid particle also without forming. This one we can have. So that's why this insulation helps a lot of people in the western side. They are able to get the thermal insulation. But for us in space, we are insulating the liquid hydrogen tank and liquid that is in 20 Kelvin or liquid oxygen tank with this polyurethane foam material, so that we are able to maintain the 20 Kelvin and the like hydrogen gas I was telling, it's not getting evaporated. So insulation we are able to make it. So these are all the properties. One is that it has to withstand the high thermal gradients of 20 Kelvin, and outside when the launch vehicle is moving at a high speed of about 2 to 3 kilometers, a lot of heat will be generated on the surface because of the dynamic pressure as well as the atmospheric gaseous molecules. So it has to, polyurethane has to see the window, nearly 500 Kelvin it has to meet. So then compressive load has to meet, then aerodynamic load during the flight, thermal cycling, because if there is a launch call off, no, we'll have to drain the liquid hydrogen and again refill it, we refill it, so that causes thermal cycling. So this also it has to withstand. So polyurethane is one of the finest materials. How we are making is that the raw materials analyzed, accepted raw materials, we mix it, and there is a nucleation, and we also add the foaming agent. This volume actually it is rising of the foam, then gelation takes place. After curing, it is able to maintain the rigidity, closed cells, then the volume has gone up, so density is very low, and thermal insulation is brought about, right? So next, this is what is the cryo insulation system on the tank. We have done it. So please believe me that it is only because of the carbon-carbon and nitrogen-carbon and carbon oxygen, 3 bonds only have give rise nearly about 30 mm insulation we are giving, and different layers are inculcated for different purposes. So here it is anti-static coating, and here it is a heat shield coating. Then there is vapor barrier coating, so that during the draining, the atmospheric air is not, because at 20 Kelvin even the nitrogen will get solidified. So this is how we are doing the insulation for this one. So this is what our spin-off for making all the foams. Every home we have the polyurethane foam, the PU foam. There's nothing but this material. This is how the spin-off has come from space development. So and this is yet another development where we have made a conductive coating. That is, one is the black conductive coating we were using. Now it was gray. Now we have made it as an all white conductive coating. So the emissivity, solar absorption, all the things we were able to meet. So it is a chemistry, and that has brought about the space technology achievements and desirability, not only for us, for the space faring the nations also. And come to yet another thing is like carbon. We have known some idea. So now it is the role of now silicon and oxygen. So silicon, if I am adding, now it becomes the methyl silanes. Now it is silicones, where alternate O's will come. So when compared to the SiO energy, now when compared to CO, SiO energy is little higher. So that way it needs higher heat requirement to get it broken. So wherever the heat comes in our launch vehicle, so we are using this silicone materials for the purpose. So you can see the silicones are getting repeated. We are using it with trihydroxysilane. So that's how the cross-linking takes place. With that, we are able to use it on the thermal protection system. So then, if I am able to make it in a flexible way, it will be vibration isolator also. And O-rings are getting formed. Flame retardant coatings are coming out from this, and higher oxidation resistance materials. And since this is having SiO bond, hydrophilicity is less, where we use water repellent coatings also. So by changing over from CO and bringing the family of SiO, we are able to inculcate this kind of various parameters. You can see the high temperature side. Earlier I was showing 100 for carbon. Now it is 350, right? So it is because of the bond energy that we are able to increase from this level to the 360 for going to 450 makes the temperature capability from 100 degree for other carbon based materials to silicon material 350. So now modification also can be carried out. Like we can add benzene rings for various purposes. We can use this one as a coating over silicon adhesive over the CFRP panel. We can use, and again the Kapton top layer will come. Then cyclic silicones also we can bring in for various applications, so that the high temperature applications up to 1000 degree we can use with the filler materials being there. So like that, the value addition can come in chemical materials by doing versatile changes. So making the bond and breaking the bond, only the chemical people can do. That's why when it comes to relation also, people say that it's a human chemistry. So this chemistry is less complex than human chemistry. So that is what I would like to make a slight diversion. Then come to thermal control coatings. So several the payloads are there wherein it will get heated, or the internal the cooled item we'll have to insulate with this kind of materials, and hot items we'll have to protect our payloads from the hot propulsion area, or the plumes are coming. So wherein we'll have to go use these coating materials. And also there will be like exposed to sunlight, because some of the payloads in satellite will be exposed to sunlight, where the solar absorptivity, the light should not be absorbed, and also the emissivity should be higher, low solar absorptivity and higher emissivity. So now you can see all these materials. The right side you see bottom, we are seeing the tricolor. So we had the pleasure and we had the honor of hoisting this one, which was made using the silicone materials, with the dyes being there, as well as the white color and green color with our great Ashok Chakra. And this flag was hoisted on 15th August of 2022, and we all had the assembled at a particular time, and the chairman was with us. So we had the pleasure of making the coating and bringing it out and hoisting it at a particular time. So there also the chemical materials and the chemistry played a very great role. I come to polyimide. As I was telling now, so these chains are now changed. You can see double the CO bonds, and this one can form a film. So dianitrate and diamines together can form a film. This is the type of film that we can use. So this film is only giving the protection for the total satellite here, and also this, if this film is made into a tape, if you are winding over a mold and then the mold can be removed, then it becomes the pipeline. This pipeline is the one which gives the fluid line, forms the fluid line for the LH2, that is in liquid hydrogen condition. Also this will be the pipeline which will give the, because from tank it has to come to the engine side. So this is the one which provides, unfortunately when it goes to low temperature, the strength of the material also goes and the flexibility is not affected much. So even at 20 Kelvin, the chemicals and chemists will be flexible. Please keep it in mind. Okay. So now comes to the phenolic resins, where see like these materials now, whenever there is a heat that is coming out, when we are re-entering for the future, once we are going to space, coming back is uncontrolled system. So when we are coming back now, there a lot of heat will be generated. This is the one module which we recovered because of the phenolic resins gave full protection. You will see no damage. How it is giving the protection means when it is entering, a lot of heat will be formed. That fortunately these materials which are there, it will because of the heat, it will get decomposed and take the heat and it will get decomposed. You can see the substrate. This is the virgin material. This is the pyrolysis layer. Here it is a reaction products. The reaction products means it will be continuously undergoing reaction and it will be taking out the heat so that the internal materials and the crew will not be getting the heat of heat and the destabilization will not be there. So this is called ablative TPS, ablative thermal protection system. Good ablation properties are to be there, but up to certain level it should have thermal stability also. So this is achieved through a catalyzed condensation. So now this is epoxy material. All of you know about the araldite which I have shown. So here it is the hydroxyl group and the epoxy which will react and it will give rise to a very strong bond adhesion, but low temperature conditions we will be able to. All our the motors, that is the composite motors, we have the fiber bound and the fiber is held in position by the epoxide molecules. So we can have several composite materials, several composite structures which will be able to withstand the pressure or the strength it will be able to offer. So that way we have the epoxy resins in place. Then it is the ceramic materials. See, like even the ceramics now, polymer derived ceramics. So ceramic, what I'm saying is that it should be silicon carbide, so that the temperatures above 350 or 500 or 1000 up to 1200 degree, if you have to go means, and 1700 we have touch means, again whatever be the polymer or carbide or phenolic resin will not be able to sustain. Then we'll have to use metallic carbides like silicon or zirconium or hafnium. We will have to undertake this kind of materials. So, but these materials we can directly forming the silicon carbide is a bit difficult. We use different heteroatoms, and these heteroatoms can be derived from a polymer material. So, like polycarbonylene kind of material we will start with, and the silicon will be there, and the polymer matrix. This kind of different materials, if you are invoking for the reaction, we will be resulting with the silicon carbide coated onto the structure, because these are all the nose cap. And this is the like wing, the leading edge will have a high temperature of the order of 1500 or 1700 level here, will be met by silicon carbide. Even to form that, again polymer materials are coming into picture. This is with respect to composite, which I was explaining to you. Different type of composites are there, so which we can make use of. So polymer materials as well as the metallic carbide materials are handy, so it gives rise to a synergetic effect. So let me go to the carbon fiber. For satellites, we are using it motor case, nozzles, liners, and high strength as well as modulus is offered by the carbon fiber materials. Again, it is coming out from a polyacrylonitrile. Carbonization, it gives carbon fiber of very high order of strength as well as modulus. Then it is the ceramic matrix compost which I explained. So these are all the different carbide materials, carbon matrix, oxide materials, borides, carbides, all of them are there here. So all these things are derived from a ceramic matrix composite, which is using the polymer ingredients. Okay. So now the shape memory polymers are also there on the triggering it with temperature or with some of the voltage or heat. We will be able to also make the shapes that are getting formed in situ. So that these materials, we don't need to have mechanisms carried, combustion mechanisms are not required. So just give an input of heat. This will undergo the variation in shape. So they are only called shape memory polymers. So self-healing, I was explaining earlier. So I don't want to get into it because paucity of time, I'll move a little further. Now the other materials where, see now we are fabrication, mechanical fabrication calls for a lot of time consuming, measuring out, making the form, a lot of wastage, all these things are coming up. So instead of that one, if we use some of the chemicals and metallic materials, we make this 3D drawing and then subject it to like this kind of selective layer sintering process, we will be getting the tank itself getting the additive layer can be localized way we can form it. So we don't need to take a block, measure it out, all those things. So these are all forming this kind of structures will be very cumbersome thing. So simply print it. So manufacturing becomes very easy. Additive layer processing gives hand. So from the design shop to material, manufacturing by additive layer processing is easier. These are all the upcoming methods. Surface treatments also will give you better systems. And there are so many materials which can be used or adopted for adhesives and coating requirements. Yeah, this is yet another polymer matrix where we will use the matrix which can be adopted for our the reinforced composite fiber-based reinforced solar cells are also there. So this kind of mechanisms can be adopted in terms of solar panels on which solar cells are bonded. Even here, this was shown to you. Why we are adopting this one is the composite materials one provide very high strength to weight ratio. For the lowest mass, highest strength we will get. So the metallic materials, no. See, for certain things, structural aspects, we can use it, but the composite materials are more versatile that we can mold it or we can coat it with reduced density but higher strength, wherein the much variations in mechanisms are not there. This can be used. So futuristic is going to be like this. So even for self-immolation, because of the debris, no, we can have some reactive materials in the satellite itself. So once the satellite is running out and it is reaching the life means, automatically we can self-immolation we can activate. So no, the solid particles will be floating around in the space. It becomes complete gas. So that way we will also be able to help. So it is again the breaking of bonds and making of bonds. So without forming solid particles, so that the future is with us. So with this, let me move on to energy storage systems. See, without electricity, nothing will move. Time-wise. Okay. So the electricity is stored by the chemical reactions, and the chemical reactions like what we were having the oxygen and reductant together, but in battery, no, it's a device that converts chemical energy into electricity. All of you would have come to know about lead acid batteries or car battery, at home UPS battery, bike battery kind of. There will be two terminals wherein there will be positive and negative terminals. So it is nothing but the oxidant and reductant are stored either in the cathode or oxidant. As and when we increase the electricity voltage, it stores. Like a cell phone is the best example. All of you must be involved in that. So it is two terminals. You give 5 volt, the cell phone is getting charged. So that means the chemical is getting converted from the electricity that we give. And once you put off, automatically the stored energy is coming out as electricity. So especially for satellite, this becomes life limiting primary source of power for the satellites during the eclipse period, especially when it is running. No, when the Earth comes between satellite and sun, it will be passing through the eclipse, wherein the battery will be serving the purpose. You can see here, sunlight is there, and the satellite will be rotating around Earth. So in this period, here and all sunlight will be available. So in this period, we will be getting the energy from sunlight. But this period is the eclipse one where battery stored energy will be there. So it becomes a primary source. Even there is suppose reduced sunlight, the battery will be able to give. So now cells are getting converted into a bank of batteries in the satellites. So different systems are used. Like launch vehicle, we use battery, supercapacitor, supercapacitor, and for spacecraft, solar cell panels, rechargeable batteries, and fuel cells are employed. And wherever we are not having the sunlight, we employ radioisotope thermal electric generators where the nuclear materials are continuously undergoing decay, giving heat energy, and one cold, one hot ends of a semiconductor produces electromagnetic force, and we will be able to get the electricity generated. So these are all the major systems which are involved, like solar cell, fuel cell, battery, and supercapacitor are the main systems which are coming up in the even for the electric vehicle we will be able to use. So this is how a solar cell is working. Sun energy, electron is ejected, negative and positive will be there. So energy will be coming. So whenever the eclipse is there between here Earth is there, automatically stored energy here in the battery will be able to deliver. So this is nothing but our International Space Station. This is another satellite. We use it for the purposes. So now a little more about battery. Battery is nothing but some of the few particles. Anode material is a particle, cathode material is a particle, electrode is also a particle. So normally I call these things are nothing but some of the particles into battery, which gains once we are putting it in the perspective of positive electrode and negative electrode. So this is the negative electrode, graphene base, positive electrode, again metal oxide base. So in between electrolyte material will be there. So the rocking chair, we call it because the lithium only gets intercalated between two layers when lithium is intercalated during charging, and here lithium it is de-intercalated. Opposite side, here the cathode, the intercalation will take place. So now the lithium ion energy is only undergoing a rocking chair kind of variation. That's why it is called rocking chair batteries. So now these are all the reactions, don't worry. So charge time and voltage, this is what is the efficiency it is calculated. So we'll have to ensure that these two materials are in the right perspective, and the cycle life is met with. The resistance between the two electrodes should also be reduced. So this is yet another form up to about 2000 cycles. Again, what I want to say is this is in a different perspective of chemistry, wherein bond making and bond breaking is taking place entirely in different electrodes. In between it is a charge that is getting moved. So that is what is versatility of the batteries, where bond breaking and bond making is coming. So these are all the advanced systems that are coming up for low temperature applications, and higher energy density is another point, and the primary cells are also there and secondary cells are there. So now the future, like if all of you must be knowing about the electric vehicle, the country is poised for getting into electric mode, so that carbon dioxide we are not using from the thermal power stations. Suppose these are having some issues. All of you would have seen your cell phone bulging, some of the cell phone getting heated, some of the laptops catching fire. It's all because of between these two there is a dendrite that is getting formed. So since it is liquid only, that kind of a thing is there. Suppose if I go for a solid, where in place of liquid, that has got a very high stability. So the future is going to be with solid state lithium batteries, where we can touch the energy density very high. That means mass will be very less, and the size also will be very less. And we not only that, we will be able to get 15 years or 10 years of life. So in between, lithium sulfur also will be coming and giving hand for us. So solid state is going to be the future. So this is what is the roadmap. 1970s, 1990s, energy density is continuously going up, and by 2030 we should be promising you the 400 watt hour from present about 200 or 150 watt hour. Now that we have reached about 300. So this is the order of the day, with the number of cycles also higher for the. So again, chemistry is the one which is prevailing thing. Supercapacitor, as all you know, the people call the fixed capacitor, wherein we'll get about farads to the order of 1/10 or something like that only. Here, because of the surface area is involved from material and chemical is involved in the liquid form, we are able to generate so much of dipoles or dielectric materials. So we get of the order of about 1000, 1500 farad for sudden release of energy. Like if you see battery and supercapacitor, battery will have energy, but power, mass, cost, lifespan, fast charging are all very limited. Come to supercapacitor, all other things are good, but only thing, the energy will not be there. For short duration applications, this will be the best. If you see this curve, lower the energy, higher the power, higher the energy, lower the power. So this is how things are getting. Suppose if I can combine these two, excuse me, power and energy, automatically nothing like that. So here is the one which we have done an innovation with respect to combining. This is the battery. If I can combine the positive electrode of the supercapacitor and the positive electrode of our battery, then negative can be also tuned in line with this one. So we will be in a position to hybridize the internally a single system that is called supercapacitor plus battery gives you supercapacitor. So wherein we will not lose the energy much, at the same time we will be able to get the power, high power. So this is a new system which we brought out, which will have the same configuration of the battery. So this is nothing but charge discharge pattern we are having. So I always remember that the tortoise and the rabbit story, all of you know. Tortoise used to go very slow but steady like a battery, but the rabbit will go fast, but it was sleeping sometime, then it lost the race. But now in management parlance, using both is the management parlance. So now in ground, we can have both of them. So now tortoise can sit on rabbit, he can go fast. But in water, no, wherein we need energy and recharge, the tortoise can be carrying the rabbit. So finally, both of them will reach the finish line. So this is what is the management parlance. That is what we have done. Incorporated supercapacitor concept as well as the battery concept. So now here they were losing, but you can see they are on course to win. So it's a win-win situation if we combine the capacitor and this one. So fuel cell is one thing where we will have continuous energy, where we don't have the option to recharge like radioisotope. No, for Apollo mission, for going to moon and coming back, the fuel cell was the only thing which was used. So this is also very highly coming up. Hydrogen and oxygen we have to use in gaseous form. So if we can store separately like our petrol, then we can continuously feed and we can recharge faster. So now let me go to the analytical methods. I'll take a few more minutes. So wherein this is very essential that we have several materials like metals, alloys, propellants, pyro, foam, adhesive, energy material, thermal protection. So we use different techniques. Like if there are a variety of coatings are there, we can use GDOIs kind of materials. And the techniques, we can see the top layer is copper. Next there is nickel. Then the base material is made up of iron manganese alloy. So this is what is one of the techniques in analytical, again chemical methodology. So this is about coefficient of thermal expansion. So materials when they are put into use, no, they will undergo like expansion, contraction, that we'll have to have the measure. Otherwise, we will not have a control. So that way the thermomechanical analyzer helps us in understanding with respect to temperature, how the dimensional changes are taking place. Then come to different type of materials like aromatic hydrogens. The hydrogen peak will be coming here. And when it comes to like hydrogen here, this is not bridged. Actually, when it is held with carbon, we will have the peak here somewhere around this 4 ppm level. And when this is already bound, but not directly to the carbon, then we will have somewhere around the 4.5. So the energy level keeps coming down, means automatically we will have this kind of a picture. So we have NMR as the one which is for the phenol formaldehyde we are showing you. Then morphological things also plays a role. See now like about 1 to 10 micron, we have to get the particle size of our aluminum particles or ammonium, the perchlorate also. We have methodologies to understand. So again, I'll give a glimpse of spectrophotometers which are employed like to identify the crystalline inorganic polymers, then identifying the identification of the polymers, this one through Fourier transform. Raman spectrometer, for which our Sir Raman got the Nobel Prize now. So there it is fully employed for different variety of inorganic characteristics of the material. So this is XRF, we can directly get the composition of alloys from the surface itself. Then this is ICP, wherein the inorganic materials can be used, that is directly with respect to the different composition of materials. This NMR for solid materials, FT NMR we can have. ICP is there, ion chromatograph is there. So now I'll move these around examples for different purposes which we are using it. So now coming to, then there is a major advantage. Without analytical chemistry, we cannot do anything. Without, see, suppose if you are going to moon or collecting the moon soil or Mars soil, means we will not know. Without analytical chemistry, it will be, everything will be Greek in Latin, the Greek and Latin only. So now we will have to analyze, means it has been very paka way, it has been analyzed through our analytical chemistry. So Mars surface chemistry, it has got more silicon, the more option is there. But here, if you see in at the lunar surface, we have a lot of other materials are there. Magnesium not at all is there in the Mars. We come to know only through analysis. Then how we will, what is the benefit? Everything we will be coming to know only through analysis methods. So this is with respect to queries like how the life was getting formed. Also, you will be able to understand. So now the analyzing the environment in any planet, no, that gives the background information like millions of years, billions of years. Then carbon dating when we are doing also. The life is fully based on CHNOPS, that is carbon, hydrogen, nitrogen, and oxygen, phosphorus, sulfur based materials are the one which form the fundamental blocks like our body also. So now we come to know from the nature of the materials available how the evolution of life would have taken place, whether life was there in the moon or Mars also we will come to know. So our expedition, whatever we have done through our Chandrayaan or kind of thing 1, 2. So when the probe was hitting, we were we are the first to know that the presence of water or voice-bearing materials are there. Only the MIP, the moon impact, the probe was able to get it. So like this, this is the spectrum which was unequivocal. That unambiguous way we were able to identify that water presence in the moon and Mars also. We have these were the scientific goals that were set. Then achievements what we have done is that the argon in the exposure of the Mars is there, plus carbon dioxide in the atmosphere of Mars, no, around 270 kilometers. Carbon dioxide is also found out, and we have a ambitious plan with respect to have a wet chemistry analysis in the moon. So we are developing a payload, so in which we will be able to get the electrochemical aspects of materials. So now, what is this spectrophotometer means? How we are getting to analyze if there is an electromagnetic radiation and if it is falling onto that and we are getting the spectral lines from the surface of the Mars, automatically a spectrophotometer will be able to analyze the light that is coming out, whether what is the absorption, what is the emitted light, then we will be able to split it, and from the splitting the detector will be able to give the signature with respect to corresponding materials. So determine the elemental composition in the lunar soils or kind of things. Alpha particle X-ray spectrometer will be helping us. So this kind of analysis, this is only one of the tip of the iceberg. So now I'll take only a few seconds. This is with respect to life support system what we have developed. So if a human is there in the space, means these are all the requirements that are to be met with: pressure, water, food, air, and temperature it has to maintain. And chemistry plays a major role in this one. You can see the oxygen and the water portion, then how the sweat will be dealt with, how the carbon dioxide is removed, all the things the chemistry plays a role. So this gives you a kind of typical but complex picture I am giving you. So I am not loading more and more, but the regular life with respect to oxygen, the provision, and nitrogen also should be there, and how the carbon dioxide is removed. Now we are regenerating the catalyst with respect to doing it. And there are a lot of waste that will be generated by human beings. No? So one is that the solid waste will be there and liquid waste. Then there our colleagues have come out whether the urine can be recovered. That is all the items which are so that we can reuse the material. It should be bacteria free, and the other excretions also should be completely removed. So there also we can think about. So role of chemistry comes in environmental monitoring and atmospheric management and water management aspects are fully dealt with for the life support system by the chemical aspects only. And this is the one where we can also, using the electricity that is coming now, we can use water, generate hydrogen and oxygen using the electricity, and we can also use the water for using the human beings. So that way, a fuel also can be, fuel oxidizer can be generated using the energy available in the space, that is light and or power. That's also possible, that is breaking and making bonds. Okay, so this is air vitalization through carbon dioxide, the management, as I was telling, the lithium hydroxide, how it is playing the role. So revitalization also we can do. So water management is yet another thing wherein we will be able to recycle nearly about 6,000 liters of water is being recycled in the ISS. There is a standing example. So our colleagues are also working on that. So coming to the role of understanding chemistry in this one, even the International Union for Pure and Applied Chemistry, the top 10 emerging technologies for the 22 last year is one is the related to batteries, biology, aerogels, again the material, fluorescent sensors, solar fuels, right? So like that, the chemistry is enabling all sorts of, becomes a central science in my view to see that all the applications are served. So with that, let me show you, there is no universe without chemistry. So you take it, any stellar variations or anything without the materials being understood, it's not possible for anybody to get to understand the stellar universe also. So chemistry has got a big role. So let me thank you all and offer you best wishes. And this is at this juncture, let me thank VSSC and ISRO, the authorities, management, and the start team was behind me. So I have to really thank them for giving me this opportunity to meet you all through our the channel. So this is one of the innovations that we made through chemistry, and ISRO was helping us, giving us full support. VSSC garnered the President's Prize for this novel, innovative supercapacitor and supercapacitor, as our Saravanan was mentioning. So our ultimate aim is to that the chemistry should be able to make the smart nanocomposites for the heart, artificial heart. So the left side is the silicon, which was hoisted in space. Thank you so much. Thank you indeed very much. All the very best to you, everyone.